Hello and welcome everyone back to another video regarding arcade cabinet joysticks and how they can be modified to become controlled regarding their 4-way and 8-way restriction by software and electronics. Last time I showed you in the video about the mechanical setup that basically consists of two 3D printed parts and a servo, and how they can be attached to a standard joystick. Today I want to focus about electronics and especially how the mechanics can be controlled by software. First of all, we need of course some kind of controller where the hardware gets attached to and which handles the communication to the host computer and the software that runs on it, especially some kind of emulation software or front end for the emulation. And when we're talking about connecting hardware to some kind of computer, we always talking about kind of interface, which means there are two sides that need to be considered. The one side is the hardware itself. This is this piece of controller that I explained to you in this video, and the other side of course is the attached computer and the software. I thought it would be less effort to get this interfacing done if we can concentrate on just one side and find a way somehow that the other side, the host computer side and the software side on the host computer, the emulation side, don't need much of effort, because most likely there is some existing type of interface that we can reuse, let's say. But first things first, the controller that you see here is called Teensy 3.1. It's basically some kind of processing unit, some memory, random access memory, and a lot of I/O pins where we can attach hardware to, and of course some kind of USB port where we can get the connection to the host computer. The Teensy is a good choice for this purpose because it is, at least I am only aware of this one, who is capable to become programmed to work as any kind of USB hardware. This is not necessarily given by any of comparable microcontrollers. There are a lot of Arduinos out there that have different kind of processors and capabilities, but even special Arduinos are only capable to act as an USB keyboard or USB mouse. But what we need here is a kind of interface, USB interface. It's called ROH, Human Interface Device, ROH, HID. And the only processor I'm aware of, or microcontroller I'm aware of, is the Teensy family. Maybe there are others, but I don't know them. They are quite common and not too expensive, and as already said, easy to program. What you see here is a minimalistic setup. We have here the joystick with the servo on the bottom, and there's already the lines attached to the microcontroller. It's very easy. There are 3 lines from each servo. It's the ground, the 5-volt voltage, and the signal line. The signal line is where the information goes across, that tells the servo which angle it should get into. And yeah, Teensy has a couple of I/O pins, and even more than we ever will need for this purpose. But I have some ideas how we can make use of the additional I/Os. But as already said, this is a minimalistic setup. The ground goes to the ground pin of the Teensy. There is 5-volt or USB voltage where the red line goes to, and as already said, the signal line is attached to pin 20. That's the least thing we need to do to get this thing controlled, at least by software. And I have it already installed with the computer, and just give a short introduction. As you can see, when I click the software on the PC, the servo moves, and there's an indicator LED on the Teensy that signals that something's going on. But as already said, there are a lot of more I/O pins that we can use, and it would be a great idea if we can have attached some hardware switches that allow us to also control the orientation of the servo not only by software but also by the hardware switches. I made a very simple PCB here that consists of two hardware switches, two LEDs, and these are resistors for the LEDs, so they will not get destroyed by the 5 volts. Some very basic wiring at the back side of the PCB, and I have attached the wires with some connectors at the end. And let's connect them also to some of the free I/O pins. I used those that are next to the pin 20, it's pin 90, 18, 17, 16. And we need another ground. There's one more available that is, I think, here in the middle. I hope so. Yeah, right. As you can see, there's already a light going on, and what I using this for is just to have an additional to the software control, a hardware control by pushing those buttons. And I thought it would be a good idea to have some indicator lights that indicate the current position. As long as the joystick lies here on our desk, it's easy to recognize the orientation, but once it is installed in a cabinet, it might become difficult to know whether it has the right position. Furthermore, this kind of setup allows us to let the orientation or restriction for 4-way and 8-way be controlled by software automatically, but if we don't feel okay with it, we always have an additional option to override it by pressing the hardware switches. And by seeing the indicator LEDs, you're always aware of the right orientation. Well, in general, we of course want to have the servo stick controlled over software. What is already possible by the USB port, which is where it is connected to. I have here two sample applications just to show that it works. We have here two buttons, set to 4-way, set to 8-way, and it works perfectly. And this is the command line utility, Joy Tray, you might have already heard. And this works also. You can also use the command line, and also the server changes its orientation. And of course the Teensy provides a number of I/O pins, and therefore we have the possibility to also attach switches, hardware switches for direct control, and also to have the comfort of setting or working with indicator LEDs so that we are aware of the current setup. And as you already might noticed, the software control also has an impact on the indicator LEDs, and the same thing is valid for the hardware switches. And of course we need to have some software that runs on the Teensy to handle all the communication between the USB port and all the attached hardware, the servo, the switches, the LEDs and whatsoever. This kind of software is called firmware, and you're in a comfortable situation that you have predefined available firmware that you just need to download as one file and upload it with some utility. And I'll show you how you need to handle this. First of all, you need the firmware file. You find it on the Thingiverse page of the thing. Just go to the Files section, and when you scroll down the list, you will find the file that goes by the name tus428.hex. Just download it. Furthermore, you need the uploading utility. You find a link to it on the description page. Teensy Loader. On this side you have the choice between several versions depending on the operation system that you are using. As I'm using a Windows machine, I go there, and you find the download link to the upload tool right here. We download it, and
for ease of use, I just copied the both files in one folder here. We start the uploading utility called Teensy. It just looks like that. There's a short workflow. We start with opening the hex file that contains the firmware by clicking on the leftmost button. We select our firmware file. Open. Once this is done, we need to follow this instruction here. We need to press hardware key on the Teensy. It looks exactly like on the illustration here. I will do this here. Once this is done, in the toolbar you get two more buttons that we need to press. The first one uploads the firmware file, the hex file, to the Teensy. I click on that. Download complete. And finally we press on this button, which does reboot on the Teensy. And that's it. Basically, that's all you need to do to upload the firmware to the Teensy. And just for the case that you are a little bit interested in what is inside of these firmware, I will give you a short insight. This is not really necessary to understand. It's just for the case that you're interested in. Well, and most likely you will be surprised that just a couple of lines are necessary to handle all the stuff. It's not more than 66 lines of code. What we have here include of a library that helps us to communicate with the servo hardware. We have some definitions that we want to use over the code. Basically, we want to have some names for the angles that we set the servos to, and also have some given names for the I/O pins that we want to use. We need the servo object that is derived or based upon the library that we included, and that helps us to communication with the servo hardware. Then there's an initial setup routine. The code that is provided in the setup routine is executed once after the Teensy is powered up, and it basically initializes the hardware, especially the I/O pins. It tells which I/O pins we want to use in what way, whether the I/O pin is used for input of information, basically the switches are inputs, or output, the attached LEDs are output, or also the servo line where we control the servo is an output line. Furthermore, we give them some initial values for proper initialization. And finally, the last instruction in the setup routine tells the servo object which I/O pin we will use for setting the orientation of the servo. The next piece of code is a definition of some internal buffer, data buffer, as the instructions that we will receive over the USB port from the host computer, basically the software that is running there, most likely some kind of emulation software or front end for the emulation. Those instructions are received as byte sequences, and therefore we need some data buffer. The byte sequence that is necessary for controlling the servo stick are just 4 bytes long. So, but we declare 64 bytes of code because this is the standard package size for so-called raw human interface device hardware, and this is the type of hardware that we have here. What we try first in the loop, by the way, this is the main loop. The main loop is executed over and over again for the whole time the Teensy is powered up, just right after the setup routine was performed. And the very first segment of code within this main loop handles the USB communication. The first line here looks at the USB communication channel, whether we have some new instructions that we need to perform. If so, the instruction will be stored in the buffer that we declared, and also we get an indication of how many bytes we received. And for the case that no bytes were received, of course there's nothing to handle. Therefore, the next line asks whether we have a valid instruction that we need to perform received from the USB port. First of all, we want to know if this was at least 4 bytes of code for the instruction. That is the length of the instruction for the servo stick. And if so, we check what the value is of the first byte that we received. The first byte must be a 0 value. The second byte has to be an hex DD. The third byte has to be again a 0 value. And the fourth byte is either a 0 or a 1, depending whether we should set the servo stick into a 4-way control position or 8-way control position. 0 indicates a 4-way, while the 1 indicates an 8-way. For ease of reading and processing, we translate this fourth byte into something different. We say we have here an integer value that we set either to 8 or to 4, depending on the instruction that we received. And with this information about the orientation out of 4-way, we call a subroutine or function that is down below. The subroutine basically receives the way we should set the orientation in this variable. It's either 8 or 4 or 8, depending on the command that we received over the USB port. And first thing we do, we set off the LEDs that indicate the position. Then we set on the LED that indicates that some servo motion is ongoing. And depending whether we have an 8-way or a 4-way instruction, we go this or this part of code. In case of 8-way, we turn the servo motor in the angle position for the 8-way control. Wait some 20 milliseconds to give the motor enough time to set its position. And finally we set the indicator LED to 8-way orientation. And in the other case, if it's not 8-way, if it's 4-way, we basically do the same thing, but just set the angle for 4-way orientation, again waiting 20 milliseconds for letting the motor reach its final position, and set the indicator LED to 4-way orientation. Last thing we do is we wait another 80 milliseconds and set off the servo motion indicator LED. So this routine is, as I already said, called for the case that we receive instructions over the USB port, but we of course also have the hardware switches installed, and that's what follows next. For the case that the switch for the 4-way orientation was pressed, we set the servo to 4-way, and once this is done, we wait till the pressed button is released, just to prevent that the servo orientation is processed over and over again. And that's basically just the same thing, but of course we do it also with the 8-way hardware switch. If this is pressed, we set it to 8-way, and again we wait that the button is released to prevent repetitive execution of the subroutine. That's all the code that handles all the stuff. There's one more thing that we need to handle. Normally the Teensy or all USB hardware has a unique vendor ID and a unique product ID that is necessary to identify which kind of hardware is in place and whether the communication should be established, and if so, what protocol has to be used. If we want to become the Teensy recognized as a servo stick, we need to do some modification in a library. Just let me look. Yep. There is some files that comes with the Teensy development environment that have some basic definitions that are used for when we use, for example, this row hit communication routines. And in this file, it's called usb.dsc.h. There is the vendor ID and the product ID, and this is need to be changed. Otherwise, Teensy will not be recognized as a Servo stick. That's basically the vendor and product ID of the Teensy, and we had to change it to the vendor and product ID of the Servo stick. Otherwise, it wouldn't run smoothly with the existing software on the emulation side. But as already said, you don't need to worry about all this stuff because it's already done, and you just need to upload the firmware hex file as already described.
Well, that's all for today. The one piece that is left is how everything can be integrated into the software on the host computer, the main emulation, for example, or some front end. Maybe that's a topic for another video. But that's it for today. I hope you found it interesting. See you then. Goodbye.